Thank you all for coming today. We are so pleased that we have just finished today a wonderful fall semester. It has been great and a great start to this school year. We're looking forward now, of course, to our winter semester. It just keeps rolling for us. But today you've come here to enjoy our final lecture of the fall. And one of our faculty who used to teach for us on a regular basis before he got to be famous over in Bradenton. Actually, he still is pretty supportive of the Academy, and that's why he's here today. But Jeff Rogers, who is the director of the planetarium at the Southwest Florida Museum, is here today to share with you some exciting news about space. And we keep getting information every week, new information about space and comets. We get to see pictures of comets and people landing on comets, or not people, but machines landing on comets. And we realize that the world is a much bigger place than what we once thought it was. And Jeff is going to be able to share that with you because he is absolutely an expert in this field. He was and continues to be a very popular faculty member and lecturer here at the Academy. So please welcome Jeff Rogers.
So today, we only have an hour and then some time for questions and answers. So we're going to have a little jaunt through the universe, galaxies, solar systems, our planet, life. We've got a lot of ground to cover. And it seems like a lot of different territories to be in, but it's not really, because there's a currency that's good at all of these different scales, a language that works in all of these different realms, whether we're talking about physics or astrophysics or the earth sciences or technology or biology. Science speaks to them all. So we're going to be able to talk science through the entire universe. And the reason we can do that it worked before. I tried it. I just restarted it. Aha! That's why it didn't work. The reason that we can talk science through these various scales and these different realms of science is something that's called the universality of physical laws, which means that the things that we've figured out here on Earth aren't local. There's a universality to them. So as we look out at the universe around us, we have atoms, and we know how atoms work. They are made of the same stuff, no matter where you look. They're made out of protons and neutrons and electrons, and we know that those protons and neutrons are made out of quarks, and we sit down in Switzerland and smash things together and say, these are the bits that make that stuff up. And everything that we're doing either confirms the way we've been thinking or pushes us off in new directions so that we have to think differently about what our science is doing and what it's telling us. So we've got a universe that's made up of stuff, at least part of it is. About 5% of the universe that you live in is made up of regular matter. Here's a little secret just between me and you. The other 95%, we haven't got a freaking clue. We call it dark matter and dark energy, and for physicists, dark means giant question mark. We can see what it's doing, but we have no idea what's doing the doing. So stay tuned, there's a whole lot more to be learned. But the stuff, that we can talk about, because we know what it's made out of, and we know about matter and energy and how they work together here. And we can look out and we can say, yeah, we know the stuff that the universe is made out of. We don't have to go to a star. We don't have to go to another galaxy that is trillions upon trillions of miles away, because the atoms speak to us. They speak to us through the energy that they send out. And every atom has its own barcode. And if you can get it to light up or bounce light off of it, if you can burn it up and see what comes out of these atoms, the atoms will tell you exactly what they are. There's a language of physics, a language of light that allows us to peer out across the universe and know what's going on. And that's what got us started on understanding the universe that we live in. It's a complex place. Galaxies upon galaxies. Last count, we've got about, 200 billion galaxies that we're able to see surrounding us in our observable universe. Each one of these galaxies made up of hundreds of billions of stars, and if our galaxy is any indication, trillions of planets and their moons. So, we look out at this complicated universe with all of these galaxies, and when we look, it would appear to be very two-dimensional. I work in a planetarium. I have a dome-shaped screen over my head, and I'm able to perfectly depict the nighttime sky, because that's what your nighttime sky looks like. You look up at the nighttime sky, it looks like a big bowl over your head, and you can't tell the distances to any of those things just by looking at them. But the light will tell you a different story. This guy was one of the fellows that figured it out, and it wasn't 100 years ago. This is Edwin Hubble. The Hubble Space Telescope was named after him. He was not working alone. He gets a lot of credit. He got a telescope named after him, but he was working with a lot of really smart physicists who began to figure out some things about the universe around us. What they were looking at, well, they were looking through that, first of all. You've got the Mount Wilson Observatory. That's a 100-inch telescope, so it's 100 inches in diameter. So this was the biggest at the time. Outside of Los Angeles, which at the time didn't have the light pollution that it has today. And they were looking at these little smudges of light. We had seen them through other telescopes before. At the time, this is the 1920s, it was believed that the Milky Way galaxy was the entire universe. That was it. Everything was inside the Milky Way, and that's all we needed. And we could see these little smudges of light, these nebulae, these clouds, and some of them looked like spirals and some of them looked like little spheres, but we had no way to know how far away they were. We just assumed that they were within the Milky Way. And then somebody figured out that you can measure the distance to them, and it all had to do with something very simple, the brightness of light. That there are some stars out there that always shine with the same intensity. And if they're always the same brightness, if you see one that's dimmer, you know that it's farther away. And it's pretty easy to figure out that if you have two 100-watt light bulbs side by side, they're both going to look the same brightness. But if I start moving one farther away, it's going to get dimmer and dimmer and dimmer, and it's easy to figure out how far away it is, give or take 20%. So, when they finally figured out how to measure these distances to these little blobs, they were shocked at how far away they were. They clearly had to be outside of our Milky Way, and this gave us a universe that was filled with not just one galaxy, but dozens of galaxies. And soon it turned out that there were thousands of these. And today, using the Hubble Space Telescope, we're counting them in the hundreds of billions. But there was something else that light was telling us. You could take the light from these galaxies and break it up into their spectra. So these are black and white versions of it. These are the emission lines from different elements that are in these galaxies. And remember, every element has its own barcode. And you can see from image to image that they all have the same lines in them. But you also notice that sometimes they're shifted over a little bit. Shifted a little bit more, shifted a little bit more, shifted a little bit more. Why were these lines not in the same places on these little spectra? It turns out that these galaxies were moving. And Hubble figured out that the farther away the galaxy was, the faster it was moving away from us. So now we have this three-dimensional universe where the galaxies that are close to us are moving away from us. The galaxies that are a little farther away are moving away from us a little bit faster. The galaxies that are furthest away from us are moving away faster still. And there was only one way to explain this. We live in an expanding universe. Wow. Even Einstein said, wow. He had this idea in his head, like everybody else did, that the universe was static, that it all just stayed still. But given this observational evidence, there was no holding on to the idea of a static universe anymore. This very quickly led to the idea that, if the universe is expanding, it must have started expanding at some point in time. What if we could take the universe like a film and run it backwards? We would see everything coming closer together instead of expanding. And if we continued to rewind, eventually we'd get to a point where everything came back together. So the universe had to have been born, let's call it in a place, at a time. And this gave birth to the idea of a Big Bang, which, by the way, was thrown out there as a joke. Hoyle says, oh, and I guess there was just some big bang and the universe sprung into existence. He was trying to make fun of the idea, but the name stuck. So we have a universe that starts with a bang and is continuing to expand this day. In fact, the expansion is accelerating. The universe is accelerating faster and faster and faster in its expansion, and we have no idea why. It goes against common sense. Therefore, we invoke something called dark energy. There's some energy that's pushing the universe apart. We don't know what it is. We'll call it dark energy. We'll get back to you on what it is. So we have these expanding galaxies. The galaxies themselves are being carried away with expanding space. The best evidence we have for the Big Bang is something called the cosmic microwave background radiation. Some very smart people figured out that if there was this initial explosion of the universe, that it had to have a lot of energy to it. And if the universe is X number of years old and has been expanding at a particular rate over time, that energy should still be here, but it would be very diffuse. But there would still be a little bit of that energy left, just spread out very thin. And they calculated what that energy level should be. And it should be at the microwave wavelength. So we look out into the universe, and sure enough, what do we find? The cosmic microwave background radiation. That modeled picture that you see up there is the energy left over from the Big Bang, spread out throughout the entire universe. And we get better and better pictures of it every decade or so. So we've got some pretty good evidence that this Big Bang happened. There are some different ideas about how the universe gets started after this bang. One of the big ideas is called inflationary theory. And it's the idea that when we look out at the universe around us, as I mentioned at the beginning, it's the same everywhere we look. It's not a localized place. Everywhere we look, even though we're looking trillions and trillions and trillions of miles out in every direction, everything's the same. The laws are the same. The rules are the same. The galaxies are the same. The idea of inflation is that the universe starts very small, but gets very big very fast. Within the first million, billion, billion, billionths of a second, the universe expands from something that is much, much smaller than an atom to the size of a grapefruit. Now, I know that doesn't sound too impressive. A grapefruit-sized universe. But given the scale that it started at, that's a very rapid expansion in a very short amount of time. Before the next second is out, the universe is around 63 trillion miles across. That's fast. That's big. And it kind of stretches out the universe. It's a lot like I don't fold laundry much, but you get the idea. If you have a wrinkled sheet and you snap it really tight and really fast, it'll snap those wrinkles right out of it. Same type of idea. This idea of inflation has been around for a while. People have been looking for some evidence of it, and just last year, a team working with a telescope down at the South Pole was looking at the cosmic microwave background radiation, and what they found was a polarization of the light. I'm not going to get detailed on that right now, but they found a signature in this microwave background that suggests that inflation may actually have happened. So we have some observational evidence that suggests that the universe did get really big really fast in that first second. The jury's still out on this. This is the way science works. They presented their data, they presented their ideas of what the data had to say. So stay tuned. Within the next year, we'll get some better ideas of whether this works or not. But if it did, and it does look like inflation explains a lot about our universe, there are lots of versions of inflationary theory out there, but every last one of them calls for not just a universe, but a multiverse. Which means that if inflationary runaway happens once, it happens over and over and over again, which suggests that our universe would not be the only universe, that there would be an infinite number of universes. Now, a crazy idea. Some of you are shaking your heads saying, bah. A lot of scientists shake their heads and say, bah. Because there's really no way to test this, because we can't get outside of our own universe to go look for other universes. But in the cosmic microwave background radiation, there are a few artifacts that we have not been able to explain yet. We find that there are cold spots, dents, if you will, in the cosmic microwave background radiation. Now, these all just started to be explored in the past year with the latest, most high-resolution version of the background radiation. But there are some who suggest that these may well be dents left in our universe from when we were expanding very rapidly and we bumped into other universes on the way. Wow. No, we cannot get out of our universe to go explore other universes. In fact, there's no reason why we would think that the other universes would make any sense to us at all. No reason why they should have the same laws of physics that we have. They could be completely different. There may be no way for us to study them. But if they bumped into us and left a dent, we can learn something about them. Just like, and I hope this doesn't happen, you walk out today and you find that there's a dent in your car. You didn't see it happen, but you can start to make some deductions about what hit your car. Was it somebody on a rascal? Or was it a four-wheel drive pickup truck? Was it green or was it blue? Was it moving fast? Was it moving slow? Get the idea? So we may be at that exciting point from observation that we get to start talking for real about other universes and that we get to know something about them. If we do, I promise you'll see this in the newspapers and on your local news. So, we have ways of understanding our universe. We have ways, and it's all based on light, that we can look out and see what's going on, not just now, but in the past. So we start to make some sense of this universe around us. We find that the stuff that we can see is mostly galaxies. And again, galaxies are these just cities of stars, hundreds of billions of stars. And here we have a picture from Hubble of a beautiful spiral galaxy. Within these galaxies, though, it's not just stars. It's also gas and dust. The galaxies themselves were pulled together by gravity. Right, so gravity is a force that all you need to get some gravity going is a little bit of mass. Any little bit of mass. You, with your puny little bit of mass, you have gravity. You have an attraction to something around you. Einstein told us how this works. He told us that space is not nothing. It is something. So we can talk about the fabric of space-time. And if you put something into space, it actually bends the space around it. So in a two-dimensional model, you can think of it as a big rubber sheet. And the heavier or more massive the thing you put in it, the more it bends the sheet. That makes a bigger hill, and that hill that's made in the sheet, that's what we experience as gravity. So here's a picture of just a gravity well in space. The more massive the thing I put in there, the more massive this hill gets. If you start with a universe that's just got energy in it. And you want to get to the point where you have all those other elements that we were talking about. You got to go through a few tricks. We won't go into all the details, but let's assume that the early universe only had two basic elements in it. Roughly, the first elements that we had in the universe were hydrogen and helium. And the breakdown was about 75% hydrogen and about 25% helium. And that was it. That was the only atoms that we had in the universe. But even if you're just an atom of hydrogen, you have a little bit of mass, which means you're bending that fabric of space-time just a little bit. And if another atom of hydrogen comes around and rolls down that hill, it sticks to you. Now there's two, and that's a little bit more mass. And over time, you get these giant balls of gas, hydrogen and helium. We call them stars. Stars work primarily because of gravity. Gravity pulls them together into these giant orbs, but the poor atoms down at the center really have a tough time of it. In physics, here are some basic rules. When you contract something, it heats up. When you expand something, it cools down. Also in physics, when we say something is hot, what we really mean is it's moving very fast, right? Basics. When you think it's hot outside, all that really means is that the atoms, the molecules of gas in our atmosphere are moving around really fast, and a lot of them are hitting you with a lot of energy, and that energy is transferred to you, and you say, where's all this energy coming from? When it's cold outside, those atoms are moving slowly and lazily bouncing off of you, and they're not giving you a lot of energy. Inside of stars, down here at the core, gravity pushes in and contracts that stuff so much that the atoms are moving so fast that they can actually slam into each other with so much force that they fuse. We call this nuclear fusion. Nuclear fusion releases energy. It's one of the holy grails for energy that we have here on Earth. So, nuclear fusion, what does it mean? Well, it means that you're taking some 4 atoms of hydrogen and slamming them together, and you get 1 atom of helium. We have a different element. What does it mean to have a different element? Well, all the elements have different characteristics, but it's all based on the number of protons and neutrons that you can get together in a small space. That will determine how many electrons spend their time around that atom, and that means that they're going to interact with other atoms differently. So we can make different elements inside of a star just by putting together new configurations of protons in the core of a star. So stars make energy, but they also make elements. And over time, the more massive stars, they start out just turning hydrogen into helium, and eventually they start running low on hydrogen, and they start fusing the helium into nitrogen. And then the nitrogen can start fusing into oxygen and neon. And then we can start making carbon, and then we can start making iron. And these big stars kind of have an onion-like look inside, and they're layered with all these new elements that were made inside of these stars. But here's the trick. After the star builds up a core of iron, it can't go any further. No star is massive enough to fuse iron. In fact, when they try, the reaction sucks energy in. So here we have a star that has lived its life, and these big stars only live in the order of millions of years. And it was a balancing act. Gravity, it's just a big ball of gas, is trying to collapse this ball of gas down into the center. But because energy is being released from the core, there's a stasis, there's a balance between the two. But when the energy in the core shuts off, gravity takes over and collapses the whole thing down into the core. And it bounces back into a massive explosion that we call a supernova. A supernova explosion shoots all of the elements that were built inside that star out into the space around it, giving us an enriched cloud from which we can make planets and moons and dogs and cats and chairs and all the stuff that we want to make. This, just so you know, is the remnant that's called the Crab Nebula. This was actually a supernova that was witnessed by Chinese astronomers in the year 1054. And then we look up into that part of the sky, and sure enough, there it is. So we have these clouds of gas, enriched gas, floating around in our galaxy. Gravity doing what gravity does, it starts to pull parts of those clouds back together again. So now we have new stars being formed in these clouds, but we've got the extra stuff. The extra stuff will become planets and moons. However, the process of planet creation can be very violent. We describe Earth's earliest periods. We call it the Hadean period. Hades, hell. The process of forming a rocky planet especially means that you've got a bunch of stuff swirling around a star. Big stuff, rocky stuff, metallic stuff, and it all comes crashing together. And the larger the planet gets, the more gravity it has and the more stuff it pulls in. But that process releases a lot of energy. And at one point, our planet, like all the other solid planets in our solar system, was molten, straight down to the core. When that happens, the heaviest elements that you have available are going to sink down to the gravitational center. The other elements are going to layer themselves up by density up to the crust. What we end up with is a planet that has an iron core. Iron is the heaviest element that's made in any abundance. Stars make big bunches of it in their cores before they go supernova. So when we look at Mercury, Venus, Earth, and Mars, we see that they all have cores of iron. This is going to be important for us later on. But first, this isn't the only place this is happening. We're now discovering new solar systems. We always had the idea that there would be other planets out there. Any science fiction fan knows that. But now we've got the technology to actually find these other planets. And to date, we've found nearly 5,000 other solar systems right here in our little corner of just our galaxy. The numbers extrapolated out suggest that there may be more than 1 trillion planets in our galaxy, and that a percentage of those should be habitable, places where there could be liquid water. Life as we know it might exist. How do we learn things about these other planets? How might we discover life? Well, we look out with space-based telescopes, and what we look for is a good lineup where there's a star, and a planet's orbit takes it right in front of that star. So kind of we call it a transit. It's like an eclipse, except the planet's going to be very, very small. We look at that star for a long time, and we know exactly how bright it is. And then every once in a while, when a planet crosses in front of it, the temperature, the light coming out of that star dips just a little bit. It might just be a pixel's worth of light that disappears from it. And we watch that go across, and we say, that star dimmed a little bit, something might have crossed in front of it. So we wait to see if it happens again, and we see if there's regularity to it, and that tells us, yes, there's a planet orbiting that star. And if we get really lucky, the light from that star is passing through an atmosphere. And if it does that, the light that we get from around that planet, remember those little lines in the spectrum, will tell us what gases are in that atmosphere, or what kind of light is, or what is on the surface as light bounces off the surface. We don't have to go to these other planets. We can tell you what their atmospheres are made of. We can tell you what their surfaces are made of if we get just the right lineup. And if there's life, maybe there's an abundance of free oxygen in the atmosphere or methane in the atmosphere. So we can start to look for the signatures of life on planets around other stars. So all of this is happening right now. Just about every month we get a new download of new planet data from other solar systems. And we can see the process of planet formation happening. We can look into nebulae, those clouds of gas and dust that are within our solar system. This is the Orion Nebula. And it's lined up just so that we can peer into it. It's kind of shaped like a big cornucopia. But its open mouth is facing towards us. And when we peer inside with our space telescopes, we see this, and this, and this. These are baby solar systems. These are stars that are swaddled in gas and dust, cocooned in it, and we can start to see new solar systems being born. Wow. The Kepler Space Telescope isn't working to do this anymore, but we've got others on the way up right now. And we look out at all the stars, hundreds of thousands of stars that Kepler looks at, and we can start to figure out which planets are which sizes. So you now live in a place where there's not just one solar system that we can talk about, but thousands of them. Back to our solar system. Earth forms during the Hadean period. It's hot. The iron core sinks down to the center, and the core remains hot to this day, probably around 11,000 degrees when you get down to that core. And that energy never stays still. Energy will always flow from places where it's hot to places where it's cool. So we have energy rising from the core up towards the surface of the Earth regularly. It doesn't come up nice and smooth in all places. There are plumes and hot spots and places where it breaks through. We see these as volcanoes. We see these as earthquakes. And we see this as the driving force behind plate tectonics. So this is the energy that's driving the dynamic forces on the surface of our planet. Because our planet formed hot, when it first gets started, there were no oceans on the surface, no atmosphere like we have today. We had too many big things smashing into us to blow all that stuff away. It was too hot for Earth to retain an atmosphere or oceans. But after things cooled down a little bit, and after the crust begins to form, it's from inside the Earth that we're going to start to see a lot of interesting things come out. Through volcanoes. Yes, lava gets all the attention. That's the sexy stuff. But we got a lot of gas that comes out of volcanoes. And amongst the gases that come out, carbon dioxide, water vapor, some hydrogen, some helium. They typically escape. They're too light for the Earth to hold on to. And a lot of nitrogen. When you have this outgassing happening, you start to fill your new atmosphere with new gases. It's not too hot, so these gases stick around. The one that's most interesting to start with is the H2O. Water vapor fills the atmosphere. But because we are the right distance away from our star, it is cool enough for that water to begin to condense, to move from its gaseous form into its liquid form. Oh, and it rained. And it rained, and it rained, and it rained, and it rained. We're not talking 40 days and 40 nights here. We're talking thousands of years of rain, filling up the depressions and basins on the surface of our Earth. As water comes down through the atmosphere, it picks up carbon dioxide along the way. You remember acid rain? That was a big thing back in the 70s. Even I remember it. I was a wee one. But acid rain. All rain is acid rain. Because all rain, all water picks up carbon dioxide, making a weak acid on the way down. So the oceans begin to fill up, but it's not just with water. It's mixing with the other stuff that comes out of those volcanoes and that's sitting on the surface of the Earth. We have carbon from the carbon dioxide that's in the atmosphere. We have oxygen from both the carbon dioxide and from the H2O. We have hydrogen, of course, from the H2O, and nitrogen is another gas that comes out regularly. So CHON, carbon, hydrogen, oxygen, nitrogen. The four elements that you need to put together amino acids. That's all you need. You need those four elements, readily available on a place like Earth, now mixing in a liquid medium. Amino acids are the things that you need to build proteins, the stuff that you need to build cells. Give me a little bit of phosphorus, a little phosphate, a little phosphorus, and a little bit of sulfur, and I have everything that I need to make DNA. The molecule of life, but not life. It's just a molecule. DNA is not alive, but it carries the information that we need to move from generation to generation. Your genetics, you're all aware, give you the ability to pass traits on to the next generation. You can build this stuff from elements that are readily available on a planet like Earth, and perhaps readily available on other planets that formed like Earth did, which could be in the trillions. So, I'm going to cheat now. And life gets started. We don't know how life got started. We really don't know. But we have very good evidence that life exists, so we're going to say it gets started. We have to assume that the earliest life on Earth was autotrophic, which means it makes its own energy. Plants do this. Photosynthesis is a way to make your own energy from sunlight, from carbon dioxide, and from water. We can look back at the fossil record, and small stuff doesn't fossilize readily. But we have these buildups of different types of bacteria. And we see things like stromatolites. These are colonies of bacteria. And what we're looking at is something akin to today's blue-green algae, a photosynthetic type of bacterial life. And here's the interesting part. This has to happen in the water. All right, so land is not a good place to start life on early Earth, because the atmosphere isn't going to protect life from the dangerous radiation from the sun. You all wear sunscreen, right? You're protecting from ultraviolet radiation that makes its way through our atmosphere. Some still makes it through. Most of it gets blocked today by something called the ozone layer. Very good that we have an ozone layer. There wasn't one then. Ozone layer is made, and we're going to take a look at this in a second, from stuff that cyanobacteria, that the blue-green algae has to make. A byproduct of photosynthesis is oxygen. What we start to see is that with photosynthetic life starting in the oceans, probably around 30, 33 feet deep, deep enough that the ultraviolet radiation is absorbed by the water, but visible light can get through. The visible light gets through, we have photosynthesis going on, oxygen being pumped out, the oceans begin to fill with oxygen until they can't handle anymore, and then that oxygen begins to drift out into our atmosphere. And when you have oxygen, the molecule is O2. This is just a regular old oxygen atom. But if you put O2 up there in the atmosphere and it gets whacked by ultraviolet radiation, it will break apart. And oxygen loves to come back together in threes. Ozone. So the oxygen produced by life on Earth fills the atmosphere, which then gets broken up, recombines to create an ozone layer, which then makes it safe for life to come out of the oceans, because now we're protected from that ultraviolet radiation. Life has the power to create global changes in our atmosphere. Keep that in mind. We can look back at the changes in our atmosphere, and what we see is, once we get life started, carbon dioxide starts to dip precipitously. Plant life taking in that carbon dioxide, water taking in that carbon dioxide. Once the oceans form, they become sinks for carbon dioxide. That carbon dioxide is later incorporated into plant life, and once we start getting to more complex life, life forms that have shells made out of carbon, it traps that carbon for a long time. So we take that carbon out of the atmosphere, we put it into other forms. It can take the form of then limestone, further locked down and kept from going back into the atmosphere. So Earth had a mechanism based on its chemistry, based on its temperatures, based on life, for taking carbon dioxide out of the atmosphere, incorporating it into living things. You've heard it before. You are a carbon-based life form. All life on Earth, carbon-based life forms. We use it. We use it to build ourselves, and we also use it to get our energy. So, life on our planet gets started. It starts in the oceans, an ozone layer eventually forms, which means that life can safely come up towards the surface. And today, we look out at the world around us and we see, hold on, I got ahead of myself, a wide variety of living things. How do we account for that? Well, that guy got us started on it, but he wasn't the first one to be thinking in these terms. Darwin's grandfather used to write poetry about evolution, which probably influenced young Charles. That hot core at the center of our Earth creates continuous change on the surface, long-term change, slow change. As continents move across the surface of the planet, new mountain ranges rise up when continents collide, new oceans open up when continents pull apart from each other. climate will change as these mountain rises and these ocean currents shift. So this long-term change, coupled with life's ability to change along with it, especially when it's long, slow changes. As these major changes happen on the surface of the planet over hundreds of millions of years, populations of living things can adjust to it genetically, to adapt to a changing ecosystem, to adapt to new shorelines, to new savannas, to new estuaries, to mountain ranges, to new arid areas that will start to form because of mountains coming up. Genetics and natural selection help us to understand how life can change over long periods of time, and why we would see such a diversity of life on our planet, because it's always changing on the surface, forcing life to adapt or become extinct. 99.9% of all things that ever lived on this planet are extinct. All life forms, give it a shot. Everything goes extinct eventually. But life has a way of passing on to another generation despite the changes that are happening on the surface. Over long periods of time, these things that were living and dying, many of them become sequestered underground. What they're taking with them, their carbon. The carbon that we've been taking out of our atmosphere, the carbon that is the basis of all life forms, many living things, when they die, become rock. This can be fossil, this can be coal, this can be limestone, this can be oil. Living things can change into geologic things over long periods of time. And then we come along. We evolve to take advantage of natural resources around us. And we learned early on that you can release the energy from once living things, trees, that had carbon stored inside of them. And when those limbs are dead, that carbon is still there, and we can start to release that energy. And that energy does us a lot of good. From that energy, we move on to say, there are other types of natural resources that have even more energy stored in them. Coals, gas, the petroleum products. So we start going after those. On Earth, there's a long-term carbon cycle and a short-term carbon cycle. The short-term carbon cycle cycles through about every 300 years or so. It's pretty much self-correcting. If carbon dioxide builds up in the atmosphere, it starts to get warmer. That's the greenhouse effect. When it gets warmer, there's going to be more water vapor up in the air. There's going to be more rain. Remember, when rain comes down, it picks up carbon dioxide along the way. All rain is acid rain. So the more rain there is, the more carbon dioxide will be pulled out of the atmosphere, and eventually you reach a nice equilibrium. But over the long term, the carbon that gets deposited deep underground, that stuff usually takes millions of years to cycle through. It relies on plate tectonics to get out of the Earth again, or to be driven down into the Earth even deeper. So we have these deposits of carbon sequestered, trapped under the Earth. These things would not normally be released until they get into a hot spot where they will get remelted and more carbon dioxide would be expelled out into the atmosphere. These things were taken out of commission for millions of years. The issue that we have today is that we have learned to tap into those sources. Sources that the planet was kind of hoping to keep underground for a little while. We're accessing them and we're bringing them up to the surface, which means that we're bringing more carbon to bear in our atmosphere more quickly than the natural systems would normally be able to accommodate. So when we talk about climate change and we talk about humans as a cause of climate change, we simply have to recognize the universality of all of this. We know how carbon works. We know how carbon dioxide works. We understand the basic workings of our planet, and we understand what happens when you add carbon dioxide into the atmosphere. That's as far as I'm going to go with that, because I don't want to get into some political debate about this, but I wanted you to understand the basics of what's happening with carbon dioxide release into our atmosphere. In the end, the planet will be just fine. It's just a question of whether changes are going to happen rapidly enough that life in some of its forms, cannot adapt quickly enough to survive the long term. So this universality of physical laws allows us to talk about the nature of our universe, the nature of galaxies, the formation of solar systems, the stuff that makes up planets, the stuff that's happening inside of planets, and even the stuff that's happening to life on its surface. And that's all we had time for today. So I thank you for taking that little jaunt with me, and I wonder if you have any questions based on the ground that we covered today. The question was, I got you up to iron, and then I left it at that. But yes, there are other elements. You need the energy from a supernova to actually form them. So the process of a supernova itself generates the energy that you need to create the higher elements, many of which are short-lived or radioactive. So yes, it is the supernova itself that accounts for the elements higher up in the periodic table than iron. The cosmic microwave background radiation, which tells us that there was a Big Bang. And we have this idea in our head that inflation happens and that no matter where we look in the universe, conditions should be the same. But when we look closely at this, what we see is that this is a picture of the entire universe, the entire observable universe. There's kind of a line that runs through it like this, and we find that there's a little more energy on this side than there is on this side, and that should not be. When scientists saw that division where half of the universe seems to have just slightly different values than the other half, they dubbed that line the axis of evil. That does not belong there. We have no good explanation for it yet. Some of the theories go back to the idea of the multiverse and the idea that there may be something outside of our universe that gravitationally is pulling things towards it, moving them a little bit faster, which means that they would have a little more energy associated with them. So this is a problem that is alive and well. You might not hear a whole lot about it because there's a lot of people scratching their heads saying, how are we to make sense of this? It may be decades before we get to the bottom of that, or better readings, but we're not going to get too much better than this, will help us, and maybe it'll just go away. And I think there are a lot of astrophysicists who are hoping it will just go away. But in the meanwhile, I get to say axis of evil in a talk about science, which makes me happy, so thank you for asking. Any other questions? Yes?
Might you just give us a little education on string theory and how it relates to the universe?
Can we talk a little bit about string theory and how it relates to the universe? Yes, and I'll try and be very brief about it. Physics has a problem. Two problems, actually. Or should I say, the physicses have a problem. The problem that we have is there are two physics. There's the normal physics, the classic physics, the physics that covers planets and moons and their orbits and me throwing a ball to you and the stuff that we see on our scales in the universe. There's a whole other set of physics called quantum mechanics, and it governs things that are happening at the subatomic scale. All right, so things that are electrons or protons or even smaller. And when you try and put those two physics together and you do equations with them, it more than doesn't work. The answer always comes up infinity, which is math's way of saying, you don't even know the right question to ask. You don't deserve an answer. Why should we have two sets of physics? Why should there be one set of rules for things at one scale, and where's the dividing point before you get to another set of rules for other types of things? String theory purports to solve that. It is a way of putting together the two physicses simply by saying that particles are not points. They're strings. And they're strings that vibrate. And mathematically, this gives us a way out of the jam, and the math starts to work. The problem is there's no observational evidence that anything out there is a wiggling, vibrating string. And it may be very difficult for us to find any observational evidence for it. One of the things people often focus on with string theory is this idea that it calls for multiple dimensions, that we have to live in a 10-dimensional universe. Don't let that bother you too much. Even if those extra dimensions exist, if they're existing right now, they're very small and they're built into the space around us and you can't get into them. What it does, the little strings can get into them and they can pop out of them, but you don't get to go in and out of those other dimensions. But mostly it's just a mathematical trick. Think back to your school days when we could talk about something, we could say, all right, we're going to take a number and we're going to square it. Well, that's essentially describing a two-dimensional square. Now we're going to take something and cube it. That's to the power of 3. Now we're looking at a 3-dimensional cube. No, we're going to do it to the power of 4. What you're really doing then is describing a 4th dimension. If you do it to the power of 5, it's the 5th dimension. And all we found with the string theory mathematics is we had to keep on raising the exponents to make the math work. And once the equations balanced out, they said, there you have it. We live in a 10-dimensional universe because the equation says so. It's a beautiful mathematical theory. We're not quite sure that it actually describes what's happening. But the reason for string theory was to try and meld the physics of the very small and the physics of the very big. Stay tuned. You're welcome. Sir.
If the Earth is expanding, it's moving away from some central point. Where is the central point relative to Earth?
If the universe is expanding, it must be expanding from a central point. Where is that point in relation to Earth? You're not going to like my answer. There is none. There is no central point. If the universe begins from, let's call it a singularity, a point, a mathematical point, which has no dimensions, or we just go into the quantum realm, which just makes it very, very small, but it might as well have no dimensions at our scale. When the universe begins expanding, space itself begins expanding, right? So there was no space before the universe begins this. And now somebody's going to ask me what the universe is expanding into. Nothing. If all space is encompassed in this super small point, all points of the universe, once it begins expanding, have equal claim to say, I was at the center when we started expanding. There is no center to the expansion. If you want a picture in your head of what our metaverse looks like, we can describe our observable universe, right? And a lot of people get hung up on this. Our observable universe would look like a sphere with the Earth at the center. That does not mean that the Earth is at the center of the universe. It means that we can look out in all directions and we can only see so far in every direction, so we can describe a sphere around us. But we know that there's more out there beyond that. We just can't see it. There's not been enough time in the universe for the light from those more distant places to get to us. So we can describe a metaverse. And lots of people have theorized what the shape might be. Look, my favorite is a torus, which is a fancy way of saying a donut. So if you want a picture of your universe in your head, picture a donut. On that donut is a spherical sprinkle. That's the observable universe that you live in. So the metaverse itself, that thing that has been expanding all of this time, may be a donut shape which has no center. Find me the center of a donut. I'll give you $1. All species do become extinct. None goes on forever. And we've actually got some time frames for different types of species. And mammal species tend to have a span of between 2 and 4 million years. All right, so humans were just getting started with that. So in terms of species lifetime, we've still got millions and millions of years, which puts us well ahead of the curve for when our sun runs out of energy. So we don't have to start worrying about any star-stopping stuff for another 5 billion years or so. So humans, just on a species level, if you just want to take the averages, let's say we've got another 3 to 4 million years. Let's call it 3 million years. That doesn't mean that we don't have something like humans that doesn't come after us. So our genes still move on, it's just in the form of what we would call another species. Now, are we doing things that might speed that process up for ourselves? I don't have a crystal ball. I can't know. Can we develop some new technologies that help us out of jams? Will something happen on Earth, catastrophic, that will affect us whether we do anything or not? These are all possibilities. So I will not prognosticate. I will not tell you how long I think humans are around for. In fact, I'm going to be an optimist. I will tell you. I think we're going to go ahead and live out our full, happy, average species lifetime. Why not? Right? None of you will ever be able to check and see if I'm right. So let's all be optimists and say humans will do just fine. How's that? Are there places on Earth where there's little enough light pollution that we can get good information from space? And if not, are we doing enough to put space-based telescopes up? There are some pretty dark places left on Earth. Unfortunately for astronomers, one of the primary places where they set up their telescopes is Antarctica. So if you want to be an astronomer, you might think you might get to go work on the telescope in Hawaii. Chances are good that you're going to end up in Antarctica instead. Part of the problem with Earth is our atmosphere, right? It's a wonderful thing to have an atmosphere, but if you're an astronomer, it creates huge problems for you. Visible light gets through. Some infrared light gets through. We get radio waves coming through, a little bit of microwave coming through. But mostly the atmosphere acts as a shield, and it cuts off everything that we could possibly know, from gamma radiation, X-ray radiation, all the other wavelengths that have stories to tell. All that other light is sending us energy as well. We need space-based telescopes. Are we doing enough? I would say yes. Right? We've got the full spectrum covered right now. We're looking at the universe in all wavelengths. Of course, we're sad to see Hubble starting to reach its dotage, but we've got the James Webb Space Telescope hot on its heels, still hoping to get it up in the air by 2018, maybe 2020. Let's say 2018, though, is when the shoot for date is. Yes, I do think we're doing enough. We're getting so much information about the universe around us. We're going to go through 2 generations of astrophysicists just to go through the data we're getting right now. So there's plenty of work to be done. We're collecting all the information we need. Yes, it's hard to see the stars from your own backyard, but you can always go to Antarctica. Any other questions? Yes?
You said earlier that at one point, shortly after the Big Bang, that the whole universe is the size of a grapefruit, okay?
Mm-hmm.
So if that contained everything at that time,
Mm-hmm.
after it expanded, where did all that stuff come from? That grapefruit was only this big.
That was a really energetic grapefruit.
Now it's much bigger than that.
Yes, so the universe starts out in that expansion. You can think of it as just about pure energy. All right, so it's not like there were a bunch of little galaxies and stuff in there. All the stuff that we needed to make stars and galaxies and planets, all that comes later. Right? We don't start making that stuff till about, 300,000 years after the expansion begins. As the universe expands and cools, then particles can start to pop out and get together and make stuff. So you start out with that ball of energy. Some of that energy translates into the matter that you see around you today. Right? And this is a tough one for people. If you start out as pure energy, how do you account for matter? Einstein said it's okay. Matter and energy are 2 sides of the same coin. They are the same stuff, we just experience them differently. Here's an analogy that seems to work for me. You're familiar with how this works. Think water. When you heat it up, it takes a vapor form. All right, so think of water vapor as being energy in the early universe. But remember, in physics, when things expand, they cool. So as the universe continues to expand, that vapor cools and it changes its state. Water vapor turns into a liquid when it cools. And expand and cool some more, that liquid can change its state again. It can become a solid. What we believe happens is you start with almost pure energy, but as the universe expands and cools, different forms of matter begin to precipitate out. Electrons pop out of this cloud of energy. Quarks pop out of it. Quarks come together to make protons and neutrons. Now you've got the basic stuff you need to make matter. So all that stuff was taking the form of energy early on. As we expand, matter begins to pop out. Not much of it. Again, only 5% of the universe we live in seems to be made of normal matter, the stuff that we count on to make our chairs and our tables and our cats and our dogs. Does that answer your question? As best I can. Can I comment on the science of Interstellar? The same thing happened to me when that movie Gravity came out, and I never saw that one either. I haven't seen Interstellar, so no, I really can't comment on it. I can tell you that I follow Neil deGrasse Tyson's Twitter feed, and he tweeted the movie and liked some of the science, not all of the science. He didn't like the fact that astronauts got into fistfights out in space. He's like, don't you have other things to worry about right now? I don't know what the plot was doing at the time. But he liked a lot of the science in it. And if he gives it a thumbs up, and he's a hard critic on these science fiction movies, I would suggest that they did some things right, but I haven't seen it, so I can't comment. Yes?
What about the so-called God particle?
The God particle. So the God particle was the Higgs boson, which they didn't want to call the God particle. Just so you know, physicists called it the goddamn particle. Because they couldn't find it. But the journalists didn't like that, so they took out the cursey part and they just called it the God particle. The Higgs boson, the God particle, is the particle that the Standard Model had to have to give mass to all the other particles. Finding it was very important for letting us know that we were on the right track and putting together just the model of all the parts. So think of all matter as made up of Tinker Toys. Remember Tinker Toys? And there's a standard set that you get, and you need all of the pieces to make things work. But that one is the linchpin, the God particle. It, like all particles, has a field associated with it, and the field associated with the Higgs boson permeates all of space, right? So there are these little bosons, these little particles, and they're all out there. They're spread out through the universe, and they have a field. You can't see it, right? You all played with magnets when you were a kid? You could take a bar magnet, and you could put the iron filings around it, and you would see the magnetic field around the magnet as shown by the iron filings. So, what this Higgs boson does is it fills the universe with this field, and different particles have to move through that field. Different particles interact with that field differently. Back to magnetic fields. If I have a strong magnetic field in this room and I throw a metal ball through it, that metal ball is going to be significantly affected by the magnetic field. If I throw a wooden ball through it, the wooden ball doesn't even care about it. So the wooden ball would be like a particle that has no mass traveling through the Higgs field. A steel ball would be like a particle moving through the Higgs field and being significantly, it would be slowed down by it. That means it has more mass. So mass, as we understand it, according to the Standard Model, is just how strongly a particle is interacting with the Higgs field. Maybe not the best analogy. Try this. Go home and run in your swimming pool. Try and sprint from one side to the other. You moving through that water is like a massive particle trying to move through the Higgs field. A dolphin makes it through much easier. Maybe you swim as well as a dolphin. I certainly don't. I am not as hydrodynamic. So it was important for us to find this particle because we've been basing the particle physics that we study, the stuff that makes up the universe, on a plan. That these are the parts that make it all up, but that one part had to be there or none of it made sense. Now there are some people who are looking at what we found and saying, well, don't go too fast. That might have not been what you were looking for, but I'm going to stick with they found the Higgs boson for now. So stars have this iron core before they go kaboom, and some planets will end up with iron cores as well. And why is it's important for so many reasons. First, if you don't have a continually changing surface on your planet and you don't have a way of recycling materials on the surface, you're really limiting your chance for life, which is a process to continue to get the resources that it needs. You're also limiting the change that happens on the surface of the planet. We also really depend upon our magnetosphere. All right, so that ball of iron spinning around inside a liquid center of iron, so we kind of live in a liquid-centered planet with a solid ball spinning in it. The magnetosphere also channels dangerous solar radiation away from the surface. We see this as beautiful aurorae up at the North Pole and the South Pole, but that's dangerous stuff that was coming to get you that the magnetosphere is protecting you from. And we go, ooh, look how pretty. We would not be saying that if the magnetosphere wasn't there. Many species migrate according to the magnetosphere. There are so many benefits that you have, but mostly it's about replenishing your atmosphere. Without that solid core, Mars has the biggest volcanoes in our solar system. Mars had to have once been pumping tons of magma, tons of lava, and tons of new atmosphere, just based on the size of the volcanoes. Mars is dead now. There's no more geologic activity. Those volcanoes have been sitting there for 1 billion years, and most of its atmosphere has just dissipated into space. So today, Mars only has 1% of the atmosphere that Earth has. Without something to continually replenish the gases in our atmosphere, we eventually just work through what we have. The long-term carbon cycle takes in some of the other stuff, and we're up the creek. You need that active geology in a planet. Question?
Why don't the gas giant planets condense further? It's a lot of mass.
Why don't the gas giant planets condense farther? Under the force of gravity? Why doesn't gravity pull them in? They're packed solid. All right, so they've reached their equilibrium. So there's a certain amount of mass, gravity starts to pull it in, and eventually you just reach an equilibrium where that's where you've got the stuff packed in, and it all balances against itself. Unlike stars, which are pumping energy out from their cores, the gas giant planets are not doing this. Consider that Jupiter and Saturn are made mostly of hydrogen and helium, essentially the same chemical makeup that we find in our sun. They're just much too small to do fusion, so it's not energy, it's just a matter of they've reached their equilibrium between gravity and the amount of matter that's trying to be collapsed. That was a very technical answer. Sorry. Question in the back.
What might we learn from the comet that we just watched the Europeans land on?
What might we learn from that comet? Well, here's one thing we learned. Go humans. That was quite a feat. I can't get a picture to line up right on a Word document, and these guys nailed a landing on a comet that was tumbling through our solar system. Unfortunately, we're not going to learn as much as we had hoped because the battery drainage issue. But it looks like one of the things, the information that did come out was a confirmation of something. There were organics in the cometary material. So organic molecules, carbon-based molecules seem to spontaneously form, and you don't have to have water. You just have to have carbon, hydrogen, oxygen, and nitrogen together in the same place, and organic molecules will come together. This is really interesting, right? Because comets may be the seeders for oceans, and they may deposit those organic materials ready-made on the surfaces of planets. So that's big news. What we really wanted to get into was the drilling. All right? So they're going to drill down into the surface and they're going to send us more information. What we hope to learn from comets like this is about the earliest points in our solar system. The cometary material is material that's been virtually undisturbed for 4.5 billion years, which really gives us a beautiful insight into what elements were available for the formation of our solar system. And we've got some good ideas about that. So we're hoping maybe we'll get a little spring back to life, but unfortunately we were not able to learn as much as we wanted to from this mission. But it was still an awesome mission.
How do if inflation or did they just not exist yet?
So if inflation occurred, how do the laws of physics explain this, or did they not exist? All right, so as soon as our universe springs into its expanded form, even at the microsecond level, all the laws of physics are built into place. All right, so they have to be. So how do we explain inflation? Are you concerned about the fact that it expanded so fast?
And then changed, yeah. And then, like, it seems like it went through and then really quickly and then slowed down.
It did go really quickly, and then it did slow down. Right? And now it's speeding up again. How does physics explain this? It can work mathematically. The reason the idea was put out there was to explain the uniformity of the universe we lived in. And one of the suggestions was the only way this could work is if we went really fast. All right, so we are a bubble that got big. We were a small bubble, so everything's the same because we started from a very small bit and then we expanded out from there. Mathematically, it holds and it works. The one objection that a lot of people have is, by definition, what you just told me, that expansion rate is faster than the speed of light. And Einstein said, nothing goes faster than the speed of light, except the expansion of space itself, the stage upon which light moves. So even Einstein said, it is okay for space itself to expand faster than the speed of light. All I can tell you is that the mathematics say it is possible. The observational evidence will let us know if it actually happened, and we may or may not have that at this point. That's the best I can do for you on that. We have a new temporary exhibition in the museum right now that we brought in from the Smithsonian called The Evolving Universe, which features astrophotography on a number of different wavelengths of galaxies, cosmic microwave background radiations, all of that good stuff. I am working right now and should have ready for that space just after Thanksgiving a three-dimensional fly through the exhibit. So I can take you to all of the places that are pictured in the Smithsonian's exhibition. If you like this kind of stuff, I would encourage you to come visit us every fourth Wednesday at 7 p.m. I do a program called Stelliferous Live, where we do a good old-fashioned star talk where we can talk about the stars and the planets and the constellations that you get to see overhead from your own backyard, and then a little bit of current events in astronomy, and then questions and answers. And some of them are just great fun. A lot of times there's alien questions, but I like those too. But we do this, and the bar is open, so you can get a glass of beer, you can get a glass of wine, you can sit down and you can talk astronomy with us there. If you want to take in some planetarium stuff that's purely seasonal, we have the holiday music show coming up, and it starts the day after Thanksgiving. And it's classic holiday music set to fun stuff happening up on the planetarium dome. It has no science in it whatsoever. None. All right, so you can balance your world out that way. So the most exciting things we have going on now, Evolving Universe and some new astronomy programming coming up, and the holiday music show. For those of you who may be following the museum and may have heard about the demise of Snooty, what did Mark Twain say? Greatly exaggerated. Some bad person put something on Facebook and started quite a kerfuffle. I'm here to assure you that Snooty is alive and well and happy as he's ever been. So if you were concerned,
64,
don't be. He's 66 years old right now, the oldest living manatee on the planet as far as we know. But do come visit him when you get the chance. All right. So thanks for that. Come see me at the museum.